Today I'm going to report about Doppler effect. Now, what is Doppler effect? The Doppler effect is observed whenever the source of wave is moving with respect to an observer. The Doppler effect can be described as the effect produced by a moving sound of waves, in which there is an apparent upward shift in frequency for observers toward whom the source is approaching, and he is the one who described about Doppler effect. He is an Australian. His name is J.C. Doppler.
Proposed the Doppler effect in 1842. According to him, the Doppler effect is the shift in frequency and wavelength of waves which emitted from a source moving with respect to the medium, a receiver moving with respect to the medium, or even a moving medium. In this image, we have a ball. Let's pretend it's a fire engine. The fire engine is about to start sounding its siren in a minute. We can see the sound waves propagating towards from the source. This is the sound wave created by the siren. As you can see, it travels in all directions equally. As a result, any observer on any side of the fire engine would hear the exact same sound, because the wavelength and frequency is the same in all directions, as sound waves are coming from a stationary source. The wavelength is the distance from the crest of one wave to the crest of the next. It can also be true to true. The frequency of a wave is the amount of waves that pass a given point in 1 second. In the case of this video, it is about one wave every 2 seconds. In order to understand the Doppler effect, let's see how wavelength, frequency and pitch are related. We already know that the frequency of the waves in this video are about 1 every 2 seconds. But what happens to the wavelength when the frequency of the waves is increased to 4 every 2 seconds? Speed the siren up by 2. So, if you double the frequency of a wave, you halve its wavelength. Next up is the relationship between frequency and pitch. It's quite simple. All it says is that the higher the frequency of a wave, the higher the pitch will be. High frequency is equal to high pitch and low frequency is equal to low pitch. So, the relationship between all three is high frequency equals short wavelength equals high pitch. Low frequency equals long wavelength equals low pitch. Now, we can understand the Doppler effect. The Doppler effect explains what happens when the object that is creating the sound begins to move. This time, we will watch the sound waves with the siren muted. As you can see, the sound waves are bouncing up towards the front of the moving object. They are also going further apart at the back of the moving object. This means there is an apparent change in the frequency and wavelength of the waves at the front of the object. There is also an apparent lowering of the frequency and wavelength of the waves at the back of the object. The object is still producing the same amount of sound waves, but its motion is making the frequencies and wavelengths to change at the front and back of the object. So, what would this change in frequency do to the sound heard at the front and back of the object? As we already know, the higher the frequency, the shorter the wavelength, and the higher the pitch. And the longer the frequency, the longer the wavelength, and the lower the pitch. Examples of Doppler effect. Now, let's see an example for the application of the Doppler effect. Consider an ambulance speeding past to you. The pitch of the siren increases as the ambulance approaches you, and the pitch decreases when the ambulance moves away from you. There is a similar apparent change in the pitch of the sound heard. when the source of the sound is addressed and the listener moves towards or away from the source. The change in pitch is due to a shift in the frequency of the sound waves. Doppler effect is observed in light also. Suppose a star is distant from Earth, then the frequency of the light emitted by the star decreases or wavelength increases. Thus, the spectral lines are shifted towards the red end of the spectrum. This is called red shift. Similarly, when star moves towards the Earth, the spectral lines shift towards the blue end of the spectrum. Applications of the Doppler effect. 1. Define the velocity of the speeding car. Let us see how a traffic police catches speeding motors. Short waves emitted from an observation center are directed towards speeding vehicles. These waves are reflected by the car to the observation center. By calculating the shift in the wavelength, the velocity of the speeding car can be determined. To determine the depth of oceans, we can apply the Doppler effect for estimating the depth of oceans. For this, we make use of sonar. A transmitter from a ship transmits sound waves towards the ocean floor. These waves are then reflected by the ocean floor and are received by the receiver. Note the time taken by the waves to come back to the source. Now, we can estimate the depth of the ocean by using the formula D is equal to V multiplied by T by 2, where V is equal to velocity of the sound wave and T is the time taken. To calculate the speed of astronomical bodies, the Doppler effect of light can be used to measure the speed of stars and galaxies. The spectrum of light coming from the planets and stars are photographed over a long period. By observing the Doppler shift, one can conclude whether they are moving towards or away from the Earth. To study Saturn's rings. Concentric rings surround the planet Saturn.
Let us cut this video. Let me show you about something. So here, let's start. I make some PowerPoints in my report. Let's see about this. Development. Suppose that this is an example of Doppler effect. Suppose that there is a happy bug in the center of a circular water puddle. The bug is periodically shaking its leg in order to produce disturbance that travel through the water. For example, there is water in the center and water in the for example, there's a water and there is a bug in the center of its water. The bug shaking because the bug wants to leave that water. If the word shift in, the effect does not result because of an actual change in the frequency of the source using of the source. So let me show you about this video. Suppose that there is a happy bug in the center of a circular water puddle. So let me show you this illustration. There is a happy bug who is shaking his legs, and there is a water puddle. This is a water, and this sample water puddle. A stationary bug producing disturbances in water because of shaking of his leg. Now, suppose that our bug is moving to the right across the puddle of water and producing disturbances at the same frequency of 2 disturbances per second. So, 2 wavelength per second, the bug creates 2 wavelength per second. For example, this. The bug moving to the right side, and it's create wavelength, 2 wavelength per second. So the distance of this is 2 seconds. Distance of this 2 wavelength. So this is the illustrate of Doppler effect for a moving sound source. Doppler effect, long wavelength, low frequency, and small wavelength, high frequency. When it's long wavelength, it has a low frequency. So it means when you are long distance to the sound created by anything, or waves created by anything sounds, it has long wavelength and low frequency. But when it has a small wavelength, it's create high frequency. So when you are near to that sound, it's create high frequency. That's what we call Doppler effect. General, in classical physics, where the speeds of source and the receiver relative to the medium are lower than velocity of waves in the medium, the relationship between observed frequency and emitted frequency is given. Now look at this. This is the formula given by that statement. F is equals to C plus VR over C plus VS, close parenthesis, and FO. Whereas the velocity of waves in the medium is the velocity of the receiver related to the medium, positive if the receiver is moving towards the source, and negative is in the other direction. So when the direction is to the source, it is positive, and when the direction is to the other direction, any direction, it is negative. The frequency is decreased if either is moving away from the other. Now look at this. If the speed Vs and Vr are small compared to the speed of the wave, the relationship between observed frequency and emitted frequency approximately. This is the observed frequency. F equals to 1 plus the velocity of V over C FO. Then that is the changed frequency. F is equals the previous that I showed you. C plus VR over C plus VS FO. So this question is an example of Doppler effect of that formula. A stationary source emits a sound wave of 500 Hz. An object approaches to this source with velocity of 3.5 meter per second. What is the frequency of the wave reflected on the object? Solution. In this problem, there are two Doppler shifts. The first one, because the other acts like an observer in movement and detects a wave sound of frequency. So the formula is this. F1 equals to V plus VO over V, all over V. F and times F equals 343 meter per second and plus 3.5 meter per second over 343 meter per second times 5,000 Hz. So the total is 5,051. Now the second one, because the objects acts like a source in movement that reflect the sounds, and hence the reflected frequency is this. V over V minus Vs equals 343 meter per second over 343 meter per second minus 3.5 meter per second times So that is the Doppler effect. But before we end this topic, let me show you another video that will help you to understand it clearly. So let's watch this video.